to start recording, and it's recording. I don't know where, hopefully in the right place. Okay, so it's my pleasure to have today Richard Matthews, who is a student of Andrew Brooke Taylor's at the University of Leeds. And I was really interested in this talk, so I specifically invited him to give it, and I'm very excited to hear it. All right, Richard, I apologize for all of these delays, and go right ahead.
That's fine. Thank you for letting me give a talk. Right, so before I start, please ask questions at any point in this talk, or interrupt me or whatever. So this talk is going to be based on the first half of my paper, Taking Reinhardt's Power Away, which can be found on arXiv, which is basically going to be a part of my thesis on large cardinals in weak set theories. Okay, so the motivating question for all of my work is basically this question which was posed by Reinhardt in his thesis, which is there a non-trivial elementary embedding J from the universe to itself? Now, his statement was in the theory ZFC, and CUNY showed shortly afterwards, in 1971, that there is no non-trivial elementary embedding from the universe to itself when B is a model of Kelly-Morse, so second order set theory. And this can be formalized in a first order way if we use a predicate for J, which is the standard ZFC result. And I'll sort of mention this in a bit more in a few minutes. And if you actually look at the proof by coding, this gives that there is no non-trivial elementary embedding J from V lambda plus 2 to V lambda plus 2 for any ordinal lambda. Okay, so to actually get to the question that I want to talk about today is, well, what happens if we look at a subtheory of ZFC? For example, what if we look at it without choice? This is a well-studied question, including recent work by Goldberg and Schuttenberg, and it's basically one of the big open problems. We could take a different approach, and we could ask, what if I look at it in an intuitionistic or constructive set theory? In this case, the answer is it's really horrible and quite difficult to work out what the question means, because being non-trivial doesn't mean that you're going to move an ordinal. And even if you move an ordinal, so even if there is some alpha such that alpha is not equal to J alpha, then because the ordinals aren't linearly ordered, this doesn't mean that I'll actually have an alpha such that alpha is an element of J alpha. So don't look at the question intuitionistically. Anyway, the other one we could do is we could invade weak set theory. So we could look in cryptoplastic, where you don't have any of the machinery you would need in order to prove the CUNY inconsistency. But the one I want to talk about today is what happens in theory ZFC without power set. Okay, so the first thing I should do is define the theory ZFC without power set. So under the axioms of Melo-Fraenkel, the following three principles are equivalent. Having the reflection principle, which is the statement that says, for any set A and formula phi, I can find some set M which contains A, and for which phi is absolute between M and the universe. This implies the collection scheme, which in turn implies the replacement scheme. However, it is well known that without power set, the reverse implications break down. And the implication that replacement doesn't imply collection is a well-known result by Serac. And so to my knowledge, the first proof of the fact that the collection scheme doesn't imply the reflection principle without power set is in a recent paper by Friedman, Gitman, and Knoven. So without power set, these create three different theories. So therefore, we're going to treat them all as separate theories. So I'm going to let ZF minus, with the minus being in the middle, be the theory consisting of the following axioms: the empty set, extensionality, pairing, unions, and infinity, stated standard way, foundation and separation, and then we're going to have the replacement scheme. Then I'm going to follow the notation used by Gitman, Hampkins, and Johnston, that I'm going to have ZF with an upper minus to be the stronger theory of ZF minus with the collection scheme. And if I ever at any point say either ZF minus or ZF without power set, this is going to be the theory I'm talking about. Then it's also well known that without power set, the various principles of the axiom of choice are now don't imply each other. So we're going to let ZFC minus be ZF minus with the well-ordered principle, which is the strongest of the standard versions of the axiom of choice that we use. And as a slightly different form of notation, because I couldn't have an even higher minus sign, I'm going to let ZFC minus sub ref be the system ZFC without power set, but with the reflection principle. And if anyone can think of a more consistent notation between these three things, I may use that, but yes, I'm not happy with this. So just as two quick remarks, if you use a regular cardinal, you can prove that H mu is a model of ZFC without power set, but with the reflection principle. And if we don't have collection, so if we only have replacement, then these models can behave very counterintuitively. So, for example, in the paper by Gitman, Hampkins, and Johnston, they have omega 1 exists and is a singular cardinal. Or you can have that every set of reals is countable and omega 1 exists. Or you can have the Wash's ultra power theorem fail. That basically everything goes wrong if you are assuming collection. So we would like to assume at least collection in our theory. So now it's just some of the basics on elementary embeddings. So we're going to assume that all of our elementary embeddings are non-trivial, by which I mean there is some set x such that x is not equal to j of x. Otherwise, there is obviously a trivial elementary embedding of the universe because the identity is an elementary embedding. And then there's a theorem which is one of the oldest bit theorems in terms of elementary embeddings, which is that if n is a subset of m, our transitive class models of ZF without power set, even if we only have replacement, and this even holds actually in much weaker theories like KP. And J is an element non-trivial sigma zero elementary embedding, by which I mean just elementary for bounded formulae from m to n. Then we can find an orthogonal alpha such that J of alpha is strictly greater than alpha. So the idea being, so based any non-trivial sigma zero elementary embedding of a weak theory is going to move an ordinal, as long as n is contained in m. And there are standard constructions that if n is not contained in m, then without choice, it's not true that we move an ordinal. But that's fine. So throughout this talk, we're going to let the least such ordinal be which is the critical point of J, will be denoted by either crit J or kappa. And I believe, / hope, that in all of my slides, whenever I say kappa, it will be the critical point of some elementary embedding. And then we're going to let lambda be the supremum of the critical sequence. So this is the supremum of Jn kappa as n goes through n. And this is the first fixed ordinal above kappa. Right, so as a last bit of background, I would like to make a quick metamathematical point. So our embedding J is a proper class, and therefore the CUNY inconsistency is a second order claim. So there are two ways to formalize this in a more first order way. The first one is to do what we'd normally do in a first order theory, and we'll just consider J to be a definable class, by which I mean we'll assume there is some formula phi, and J is just a set of pairs xy such that phi holds for xy with this plan, with a plan P. And we shall see that definable elementary embeddings you can quite easily show can't exist in this system. The second sort of slightly stronger version is that we add a predicate for J, which is the way the CUNY inconsistency is now normally stated. So what do I mean by this? I mean that we're going to say, we're going to take a first order theory T, and we're going to say that M is a class, and we'll assume that J is an elementary embedding from M to itself. Then we can say that M models T sub J if M models the first order theory, that is T, And it will also satisfy the replacement or collection or reflection and separation schemes of T when we've expanded the language to include J. This is not the most precise statement of this because it depends on my first order theory T on what I mean by expanding the language. But in the case of ZFC without power set with collection, all I mean here is I expand the language for my collection and my separation schemes to include J. And obviously, this statement also works if I take just a sigma elementary embedding rather than fully elementary. Okay. So first thing I'm going to talk about is a naive bound. So I want to give a bound to the naive question of, is there a non-trivial elementary embedding of a model of ZFC without power set to itself? So there are two ingredients to sort of what we want here. The first is, as I said earlier, the CUNY inconsistency says there is no non-trivial elementary embedding from v lambda plus 2 to v lambda plus 2. So then one of the obvious statements you do to weaken this, you go, is there an elementary embedding from v lambda plus 1 to v lambda plus 1? And this is known as I1, or inconsistency sub 1, is what it was originally for, because people believed this assertion would quickly prove to be an inconsistent assertion. But currently, we don't know. So under ZFC plus I1, you can prove lambda is the supreme of the critical sequence. Otherwise, there'll be some lambda star less than lambda, such that we have an embedding from v lambda star plus 2 to itself, which would contradict CUNY inconsistency. The second point is that ZFC plus I1 is a very strong large cardinal axiom. So you can prove that for each n, Jn of kappa is going to be a less than lambda supercompact limit of less than lambda supercompact cardinals. And v lambda is a model of ZFC. So what I mean by this is you can prove that in v lambda, it believes that there is a proper class of supercompact cardinals. So it is a very strong assertion to make. And in fact, much, much stronger than just this statement. It's just I can't easily phrase how strong it is without defining a lot of complicated things. Right, so firstly we want I1, and our second ingredient is the statement about extendable cardinals. So we're going to say a cardinal is one extendable if there is a mu greater than kappa and an elementary embedding J from h kappa plus to h mu plus, whose critical point is kappa. And it's worth marking here that since h delta plus believes that delta is the largest cardinal, and we have an elementary embedding, J must map kappa to mu. So it's a fact which I've been told is in unpublished notes of Jensen, and the only proof of which I know is in Andrew's thesis, that kappa is one extendable if and only if there is a mu greater than kappa and an elementary embedding k from v kappa plus 1 to v mu plus 1, whose critical point is kappa. And the point here is that we can code elements of h mu plus or h kappa plus by elements of v kappa plus 1, which is going to be how we're going to build this correspondence. So the first question I sort of asked when I saw this was, well, what if we make kappa equal mu? What then happens? Do we still get this correspondence that we can get an elementary embedding from h mu plus to h mu plus, if and only if we get one from v mu plus 1 to v mu plus 1? And it turns out the answer is we can. So that's very nice. And I would be slightly surprised if no one's done this before, but to my knowledge, there is no proof of this. So to just take the first, so I'll just sort of sketch the proof of this. So to get from an elementary embedding from h lambda plus to itself to one from v lambda plus 1 to itself, first note that by the CUNY inconsistency, you can prove lambda must be the supreme of the critical sequence. So if lambda plus actually was if we had lambda plus as a set in our model, then we can rederive the whole CUNY inconsistency. And I will actually show how you can do this later on in the talk, because it is not immediately clear that we can do it with lambda plus if we don't have the power set of lambda. But the point is, by the CUNY consistency, you can prove lambda is in critical sequence, and therefore it's a bet fixed point, and it's fixed by our elementary embed. So therefore, B lambda will be equal to H lambda, and we'll have cardinality lambda, so B lambda is a set in H lambda plus. Therefore, we can define B lambda plus 1 as the definable class in H lambda plus of those elements which are subsets of B lambda. And because this is a definable class, the restriction is going to be elementary. So that's nice and easy. The other direction is slightly more complicated. So to do this, we're going to code elements of H lambda plus by elements of B lambda plus 1. So for this, you want to just take any x in H lambda plus and bijection f from the cardinality of transitive closure of the set containing x to the transitive closure of the set containing x. I'm going to let CXF be this set of pairs alpha beta in lambda times lambda such that F alpha is in F beta. And this can be clearly seen to be in B lambda plus 1. The whole reason why I've done all of this is that if you take the collapse of CXF and the subsequent collapse of this, then you can prove this gets to the transitive closure of the set containing x. So given a set x in H lambda plus, I sort of encode it as its transitive closure of the set containing x, and then I encode that as a subset of lambda times lambda. And I can let H tilde be the definable class in B lambda plus 1 of all subsets of lambda times lambda which code an element of H lambda plus in this way. So these are going to be basically all of those subsets of lambda times lambda whose Mostovsky collapse is going to be the transitive closure of the set containing x for some x in B lambda, in H lambda plus. Okay, in many ways ignore the words on this slide. This is basically just saying that we need to define some notion of equality and elementhood for our H tilde, so that we can interpret the theory that we want to work in. So we just brute force saying this is how we're going to do equality and elementhood. And I'm not going to dwell on what these mean. All I care about here is there is some way to interpret these. So
can I ask a quick question?
Yep.
Is this just like the usual? Is this just like the usual way of like coding sets by their graph of their membership relation?
Yes, this is
great.
exactly that. Yeah.
Thank you.
But yeah, yes. So it's exactly the standard way of you encode it by its graph. Everything works nicely. So yes, so now we're going to interpret this. So if I now give you a formula phi about H lambda plus, I can rewrite this as a formula phi tilde over B lambda plus 1. And how I'm going to do this is I'm going to replace the parameter x with CXF for any bijection will do, because if I have CXF and CXF prime, they're equal tilde. So that's fine. I'll then replace instances of equality by equals tilde and elementhood by the element tilde. And unbounded quantification is now taken over H tilde. So because all of this was done in a very clearly definable manner, it respects the elementarity of my embedding K. So you can prove that if X is equal to Y, then Kx equals tilde K of Y, and similarly for element. So now we can define our embedding J from H plus by what you would expect it to be. So there is technically a slight trick here that I'm going from X to the transitive closure of the set containing X in this definition. But the point is I want to define J of X to be the collapse of K of CXF. That is what you'd expect everything to be. And then you show that if H lambda plus models phi of X, then B lambda plus 1 will model phi tilde of CXF by our coding. So by elementarity, B lambda plus 1 models phi tilde of K of CXF, which then we can collapse to get phi of the collapse of K of CXF, which was our definition of J of X. So we therefore have that H lambda plus, that J is an elementary embedding from H lambda plus to itself. Okay, so the naive question is, so if we ask the naive question of what is the strength of an elementary embedding from ZFC without power set and reflection to itself, then the answer is I1. I1 gives us a model which has this property. So what you then want to ask is, well, what properties does this embedding actually have? Does it have any interesting properties? Can I actually use it to prove anything? So the one of the nicest properties is for an embedding to be cofinal. By this, I mean that any element in N, so my range, is going to be covered by an J of an element from my domain. So for any Y in N, there is some X in M such that Y is in J of N. And just to give an example of this, well, if M and N are both models of ZF, and J from M to N is an elementary embedding, and the ordinals of M are equal to the ordinals of N, then for any alpha in N, you can prove that the embedding is sort of cofinal in the ordinals. So for any alpha in N, there'll be some beta in M such that alpha is in J of beta. So then because of this, if I have Y in N, then Y is in V alpha of N for some set, for some alpha, which is contained in V J beta of N, which by elementarity is J of V beta of M. So my point here is that if we have the nice setup in ZF, any elementary embedding is cofinal. And sort of the reason I care about cofinality is because of this theorem by Geifman, which is that elementarity can be definable by a single sentence as long as we have cofinality. So if I suppose that M and N are models of ZF without power set, and J from M to N is a cofinal sigma zero elementary embedding, then J is fully elementary. He originally proved this in Zumelo, and then stated that it can be done. The uses of power set can be replaced by using ordered pairs and collection, and this was sort of nice. This had been nicely formulated and nicely proved in the paper by Gitman, Hankins, and Johnston. But the whole point here is, if we have collection, you can state being a fully elementary embedding by a single sentence. And this is sort of the trick when they want to use to then prove Suzuki's theorem. So if I work in the theory ZF without power set but with collection, then there is no cofinal elementary embedding J, which is definable from parameters. So this gives the other naive version of this question. If we want it fully definable, the answer is no such embedding exists. So just to sort of sketch the proof. So this is obviously going to be a theorem scheme. So we're going to assert for every formula phi, we can't find a parameter p such that phi of p defines a cofinal elementary embedding. And by Geifman, we can restrict ourselves to a sigma zero embedding. So let's suppose for a contradiction that for some parameter p, we could find such an embedding. Well then, given this parameter p such that phi p defines a cofinal sigma zero elementary embedding, we can take one with least critical point, which would be kappa. And the thing is, this whole bullet point is expressible by a sentence because sigma zero elementarity is expressible by a sentence. So because it's expressible by a sentence, I can take J of it. And therefore the embedding defined by phi of J of P satisfies the same sentence. But this is critical point J of kappa, which was greater than kappa. So we've contradicted the leastness of the critical point. So it's a sort of very nice standard proof saying there's no one which is definable from parameters. But just sort of some remarks here. So Geifman's also goes to Zumelo. So therefore, if you looked at the proof of that theorem, I at no point used replacement. So in fact, we've shown that there is no definable cofinal elementary embedding for a model of Zumelo to itself. And we get that for free as well. But without power set, collection is necessary for Geifman's theorem to hold. So this gets to the first two of my annoying questions, which I can't answer. Is the first one being, are there definable cofinal elementary embeddings if I only have replacement? You would need a completely sort of different formulation because you can prove that there are sigma 1 elementary embeddings which aren't sigma 2 elementary in this theory. So it's not clear what you would do. You can also ask, well, what if I drop the cofinality assumption? So are there definable non-cofinal elementary embeddings from V to itself when V is a model of ZFC without power set but with collection? And as we will see later, the existence of these things are strongly related to I1. So if you could show that there's no definable one, you would actually, I believe, prove that I1 is inconsistent. So that's a worthwhile point to make. Right. So sort of before I talk about the main theorem and the inconsistency, it's worth mentioning an important technical point. So let's suppose that mu is an ordinal and C gamma for gamma and mu is a sequence of non-empty classes. The question is, how can I choose an element from each of these classes? If I have power set, then I just take for each gamma, I can take the elements of C gamma of least rank. This is now a set, so now I have a sequence of sets, so I can use the axiom of choice. But because these are all classes, I can't use that. So instead, we have to be slightly more careful. So I'm going to let phi be the statement that V1 is an element of C of V0. And then for each gamma and mu, there is some x such that phi holds for gamma and x. So by collection, we can take from set B such that for each gamma, there is an x and B for which phi holds for gamma and x. And we can just use well ordering of B to define a choice function or the axiom of choice or whatever you want, formulation you want, to say that so that for each gamma, we pick some x gamma. So this is just sort of a nice, neat technical trick here that if you give me a sequence of classes, I can choose an element from each class. And to sort of give you, and it's worth pointing out, collection was necessary in this statement. There are examples of models without collection where you can't do such a choice. I can give you a sequence of omega many proper classes, which are non-empty, and I can't pick an element from each class. The obvious example of this being, you could take a model of ZFC without power set bending replacement, such that you have a set of reals of size Aleph n for each n, but no set of size Aleph omega. So then so these are my classes there. Right, so just to give an example of how to use this, I'm going to give a quick proof of Fodor's lemma, also because it's needed in the proof. So Fodor's lemma states that if V is a model of ZFC without power set, but with collection, mu is a regular cardinal, S is a stationary subset of mu, and F is a regressive function on S, then there exists a stationary subset T of S on which F is constant. So just to sort of get the proof of this, well, let's assume for contradiction that for each gamma, the set alpha in S such F alpha is gamma was non-stationary. This means that for each gamma in mu, the class of clubs such that the class of clubs which have empty intersections over this set is non-empty. So by my trick on choosing from classes, for each gamma in mu, I can choose a club D gamma such that for each alpha in D gamma intersected with S, F of alpha is not equal to gamma. And then if you just take D to be the diagonal intersection of these clubs, you can prove that this is a club again. So for any alpha in S intersected with D and gamma in alpha, F of alpha is not equal to gamma, which means that F alpha is greater or equal to alpha, which is a contradiction. So it's worth out, this is just the standard proof of Fodor's lemma. The only thing was we had to be able to choose our clubs D gamma, which is why we needed this trick from earlier. Okay, so we've got all of this, and now I'd like to give you the theorem. So the theorem is that there is in fact no cofinal sigma zero elementary embedding J for the universe to itself, for which V models ZFC without power set, but with collection sub J, and for which V of the critical point is a set. This is an annoying assumption, which I'll talk about after the proof, but is necessary in the proof. Okay, so let's suppose for a contradiction that we had such a sigma zero elementary embedding. And as always, we're going to let kappa be the critical point and lambda be the supreme critical sequence. First, note that if V kappa is a set, then so is Jn of V kappa for every n, and Jn of V kappa is Vjn kappa. And therefore, by a single instance of replacement sub J, you can prove that V lambda is a set. So now there are two cases. Either lambda plus exists or lambda plus doesn't exist. And if lambda plus doesn't exist, well, because every set is well ordered, This means that for each x and v, there is some injection f from x into lambda. Okay, so case 1. This is going to be essentially Wooden's proof of the CUNY inconsistency. We just have to be ever so slightly careful at one point to make sure that we've removed the statement, the power set of lambda, which is what happens if you read the proof of the CUNY inconsistency in Cannibal, for example. But the particular one of the important parts of this is used following proof by Solovay, which is that we can partition the ordinals of cofinality omega below lambda plus into kappa many disjoint stationary sets. And again, I won't prove this, but this proof follows precisely the same proof as in the standard ZFC case, using our trick of picking from a set collection of classes. So to now actually do the sort of proof of this case, so let's let S alpha be our partition into kappa many disjoint stationary sets that we define. And we're going to let S be the collection of pairs alpha, S alpha, alpha, and kappa. Since this is a set, we can take JS. JS is now some seq pairs alpha T alpha, alpha and J kappa. And by elementarity, you can show that the collection of T alphas for alpha and J kappa is a partition of S lambda plus omega into J kappa many disjoint stationary sets. And this is just a simple elementarity statement. So what this means is that for some B twin kappa, T kappa intersected with S beta is stationary. Again, this is a standard proof, so we'll go over that. But now we can let U be those ordinals in S lambda plus omega, which are fixed by J. And you can prove that there exists some sigma. So because the U is an omega club, U must intersect our stationary set. So there exists some sigma, which is in U and T kappa and in S beta. But then because sigma is in this, sigma is equal to J sigma, and because sigma is in S beta, J sigma is in J of S beta, which by elementarity is equal to T beta. So we've proven that T beta intersected with T kappa is non-empty, which contradicts them being a disjoint partition. So the case for lambda plus is it's the standard Wooden inconsistency. It's worth noting here that this above theorem did not actually require any assumptions about J being cofinal or for V crit J to be a set. These are only needed for case 2. So this is when I said earlier that if we have an elementary embedding from H lambda plus to itself, then lambda must be the superior critical sequence. This technically follows from case 1 of this theorem. Okay. So that's case 1. Case 2 is the statement that for every x, there was an injection from f from x into lambda. And case 2 is essentially we're going to do our coding proof we did earlier. So in this case, for any set x and injection f, we're going to again let CXF be the same set we took before, which is a subset of lambda times lambda. So the collapse of CXF is the transitive closure of the set containing x. But now we have that J of the transitive closure of x, because this is an element of B, is J of the collapse of CXF, which is because of the absoluteness of the Mastovsky collapse. This is just the collapse of J of CXF, which is, so CXF and J of CXF are both subsets of lambda times lambda. So I can write this as the collapse of the union of each alpha of J of CXF intersected with V alpha. But now this CXF intersected with V alpha, each of these is now an element of V lambda. So therefore, I only need J restricted to V lambda for this collapse. But the point of all of this is I've now defined J using the parameter J restricted to V lambda. So I've given a definition of my class J using my set, J restricted to V lambda. So I've given you a definable embedding, which is a contradiction. And sort of just in case you weren't sure whether it was definable, I did write down the definition. So if I let I be J restricted to V lambda, then I could define J as this. This is just to prove that it is a definable embedding. So therefore, I can use the Suzuki proof. So therefore, we've got that. Therefore this thing can't exist. Okay. So are there any questions at this point? Before I move.
Richard, can you go
Yep.
over that last argument again from the previous slide?
Yeah, this one.
Confused.
Right. So so J of the transitive closure set containing X is by definition it's J of the collapse of CXF. This is equal to the collapse of J of CXF. And now J of CXF is a subset of lambda times lambda by elementality. So J of CXF, if we just sort of look at what's in the brackets here, so this bit is equal to this bit. To see this, J of CXF is equal to J of CXF intersected with V lambda, which is the union over all alpha of J of CXF intersected with Bj alpha. And now we can put J in there, so we got the union of all alphas of the J of CXF intersected with V alpha. So now each CXF intersected with V alpha is an element of V lambda. So I'm not actually using J here, I'm using J restricted to V lambda for all of this. So therefore I've defined J from the parameter J restricted to V lambda. Yeah. Good. Yes, it is just that, or as I've coded it as subsets of lambda times lambda, I can now break everything up and it all works nicely. Right. So the bit I'd like to sort of talk about then, this sort of last section, is I've been assuming V of the critical point as a set. Can I remove this assumption? And to remove this assumption, it turns out what we need to do is we need to assume reflection. Okay. So I'm going to use a slightly different version. So firstly, I would like to talk about dependent choice. So under ZF, we can define set dependent choice of length mu as follows. So we're going to, if S is a non-empty set and R is a binary relation, and if we suppose that for every alpha in mu and every alpha sequence S of elements of S, we can find some Y such that our little s is related to Y, then we can find some function F for mu into S such that for every alpha, F restricted to alpha is related to F alpha. So this is the statement that define every tree which has no maximal element and is closed under sequences of length mu has a branch of order type mu. So the first thing we want to do is, with our power set, we want to take the natural class version of this statement. So we're going to do the class version of this is now becoming a scheme. So for that one, we're going to replace S with some psi. And because S was non-empty, this means that for some Z, we're assuming psi holds for Z of U. And we're replacing our relation R by another formula phi. Then the next bit, so now our alpha sequence S is a sequence of elements X beta such that for each beta, psi holds for X beta in U. And we're going to assume that if you give me any alpha sequence S, there is some Y satisfying psi YU, and phi holds for S extended by Y and W. I should point out, not everyone uses this psi ZU here. Sometimes you don't state it, but I prefer it because I think it's sort of clear what's going on. Okay, but if we have both of these, pardon?
Is it the domain of the relation psi?
Yeah.
Okay.
Yes, psi is just, yes, solely the domain of the relation we're actually talking about. Yeah. So yes, psi is S for my original version. Okay, so now if we have all of this set up, then I can give you a function f whose domain is mu, such that for each alpha, psi holds for f alpha of u, by which I mean f alpha is in my original set S, and phi holds for f restricted to alpha, f alpha w. So this is, again, this is just an obvious version of translating my statement into classes. Okay. So for mu equals to L0, this concept is just the DC scheme. And as I said before, the DC mu scheme is equivalent to statement that if I give you a definable class tree, which has no maximal element, and is closed under sequences of length mu, then I can find a branch of order type mu. And one of the nice properties of this, which is not at all obvious from the definition, is that is a proposition by Levy from 1964. He proved this in the set case, and the exact same proof works here. Is that if delta less than mu are infinite cardinals, then the DC mu scheme implies the DC delta scheme. So if I give you a class tree, if I tell you that every definable class tree with no maximum element, which is mu closed, has a branch of order type mu, then that means that every definable class tree which has no maximum element and is delta closed has a branch of order type delta. Okay. So why I've sort of mentioned this is that if I go back to what the reflection principle said, well, we have by proof of Gitman, Hampkins, and Johnston, and this is the first place I know of it being proved at least, over ZFC without power set, the DC scheme is equivalent to the reflection principle, where reflection implies the DC alpha scheme for any alpha, because I've reduced an instance of the DC scheme to a set instance by reflection. And to get from DC implies reflection, well, because I'm using collection, I really only care about existential statements, and then this is just a omega sequence of picking an existential witness is what you need to do to build my transitive set N. So this is why I only need dependent choice rather than any stronger version. It's proven in a paper by Freeman, Gibbon, and Kenobi that the reflection principle is not provable in ZFC without power set. So this is a strictly stronger theory. Okay. So because of this, we get the thing which I sort of like to call proper classes are big. What do I mean by this is that if I work in the theory ZF without power set but with collection, and I have DC mu for mu an infinite cardinal, then for any proper class C, which is definable over V, there is a subset B of C of cardinality mu. So sort of any proper class is in some sense bigger than any cardinal mu. And what I shall in fact prove is that for any new less than or equal to mu, I can find a subset of C and a bijection between this subset and mu. Obviously, these are the same statement. So let's suppose this doesn't hold. Then we can let delta be the least cardinal for which this claim fails. And we can let phi of Sy be the statement that S union the element Y is a subset of C, and Y is not in S. So it's just the standard sort of way you'd use DC in this. So this obviously satisfies the hypothesis of DC delta because I'm working with a proper class. So if I give you a sequence of S many elements, I've given you a set in C, so there must always be some other point not in it. So because because delta was less than mu, DC mu implied DC delta. So therefore we have DC delta holds. So I can find a function whose domain is delta and whose range is now a subset of C. And by the definition of phi, each element must be distinct. So I've got a subset of cardinality delta, which contradicts our statement that the claim failed. Yeah. So sort of the nice corollary of all of this is now that if V is a model of ZFC without power set but with reflection, and I give you any proper class C, then I can find a non-zero ordinal gamma. Or then for any non-zero ordinal gamma, I can define a surjection of C onto gamma. Just by using that thing. And the nice property of this lemma is now if V is a model of ZFC minus with reflection, M is a subclass of V, and J from V to M is a non-trivial elementary embedding whose critical point is kappa, then for any alpha in kappa plus 1, V alpha will actually be a set in V, which sort of answers what I wanted to do at the end of the inconsistency section. So just two quick notes on this lemma. Firstly, this is basically the definition of a critical cardinal, or by Kawagila and Hayut. This is what they consider to be a critical cardinal or a measurable cardinal if we work in full ZFC. And the second point is that we didn't actually need to use either replacement or separation sub J in our assumption here. So this is not the theory Z of C minus ref with J as a parameter. This is just Z of C minus sub ref. Okay, so just to give the sketch of this lemma, so this is a proof by induction. So we prove that for each alpha in kappa plus 1, V alpha is a set. And limit cases will just follow from an instance of collection. So we now just prove these successor cases. So we're going to assume V alpha is a set. And we know that J restricted to V alpha plus 1 is always the identity, because alpha is in kappa, so alpha is fixed. Now let's suppose that V alpha plus 1 were a proper class. Then we could fix some set B, which is a subset of V alpha plus 1, and a surjection H from B onto kappa by our theorem. So by elementarity, J of H is a surjection of J of B onto J of kappa in M. But B was a subset of V alpha plus 1, so you can prove that B must in fact equal J of B. And therefore, because of its definition of the function, H is equal to J of H. Just if you plug in all the definition of what it means for X to be in B and what it means for H, what is H of X. But this therefore means that H is a surjection of B onto J of kappa, which is a contradiction because kappa didn't equal J of kappa. So therefore, our assumption that V alpha plus 1 was a proper class must be incorrect. So V alpha plus 1 is a set. And I feel that this is a slightly perverse way of proving something as a set, but so be it. So our corollary of all of this is that in fact there is no non-trivial cofinal sigma zero elementary embedding J from V into B, for which V is a model of ZFC without power set but with reflection sub J. And sort of just to leave you with two questions. The first one is, well, did I actually need to use reflection? So is the existence of a non-trivial cofinal sigma zero elementary embedding J from V to B such that V models ZFC without power set by any collection of J inconsistent? And sort of the first step one would want to do to try and prove this is my second question. So let's suppose that V is a model of ZFC minus sub J, M is a subclass of B, and J from B to M is a non-trivial elementary embedding. So I have a critical cardinal. Is the power set of omega a set? Is V of the critical point a set? These do not seem to have obvious answers. I believe the answer to both of these should be no, and would possibly follow by work on sort of what I want to go for baby measurable cardinals. I believe we should be able to be used to actually show the answer to these may both be no, which would make the first question on the slide a difficult one to answer. But I will leave it there. Thank you very much.
Thanks very much, Richard. All right, so let's see first. Are there any questions? Okay, so I have a question. You mentioned somewhere at the beginning that something would give the inconsistency of I1.
Oh, this is
because I think I missed it somewhere along the way. I think I missed the connection with that.
yes, I'm just trying to remember which slide that was.
Mm-hmm.
I would probably have to look it up one second.
Yeah. You said that the answer to some question would give the inconsistency.
Yes. Well, so the main point here was if we had a look at this statement. So this is an elementary embedding J from H lambda plus to H lambda plus. So every set X here, we have the statement that for all in this satisfies case 2 of my theorem. So an elementary embedding from H lambda plus to H lambda plus satisfies part 2 of this one. And if we actually look at the proof of case 2, I only use cofinality to be able to use Geifman and Suzuki at the end. So if you could prove that you don't need cofinality to prove Suzuki's theorem, then I wouldn't need cofinality to prove case 2. So I would be able to drop the cofinality assumption and everything else is satisfied. So I would actually have proven that I can't have an elementary embedding from H lambda plus to H lambda plus.
Right. So what that embedding is missing, the I1 embedding is missing the cofinality assumption.
Yes.
Right. So that's what I thought. I didn't have time to really think it through. But okay,
Yeah.
so that is the issue.
Yes. Well, at least you can't. I can't see how you would prove the cofinality assumption. So if I1 is consistent, then it must be missing cofinality.
So lambda goes to lambda, and then we don't. Okay. Yeah, I have to think about it. I mean,
Yeah.
it should, but I never really thought about
Yes.
it.
The issue is basically going up to lambda is easy. It's everything that happens between h lambda and h lambda plus. It's working out where anything goes there. It's not obvious. So what sort of thing? Well, even j restricted to lambda. That's an element of h lambda plus. So is there a set X such that j restricted to lambda is in j of X? And I believe that there won't be an element in h lambda plus for which this is true.
Okay, yeah, that seems, yeah, I have to think about it. I see.
Yeah.
Okay. Okay, good. And can you go back to your last slide? I want to stare at your open question.
Sure.
While people think if they have other.
I have a question.
Yep.
You mentioned ZFC minus at the beginning, and you said that was gonna be power set without a ZFC without well, ZFC upper minus where you're adding the well ordering principle.
Yeah.
But is it much different if you add? And you said without power set that maybe well ordering principle and axiom of choice aren't equivalent. Is it any different if you did ZFC upper minus with adding the axiom of choice in your theorem?
So yes. So currently I don't know the answer. If I just go back to the inconsistency slide for a second, I don't know what the answer is to this question if I am only assuming the axiom of choice in the standard formulation and not well ordering, if I understand the question. And that's basically because I don't have case 2. So it's no longer the case that if I give you a set X, then I'm using well ordering here to say X has size, the cardinality of X is less than or equal to lambda, which is what I need for case 2. So it's not clear at all how you would do the coding argument, because basically to get a model in which you have the axiom of choice but not the well ordering principle, it must be quite different from h lambda plus, which is why I can't use this h lambda plus trick I was using earlier.
Can I ask a follow-up question?
Yeah.
So would your argument here, though, work if you just had cardinal trichotomy as the form of AC you use in this context?
Yes. Yes, it should work from just that.
Okay.
I believe so. Yes.
Because it seems like that would give you your case 2.
It would give me my case 2, but I would have to check whether or not things like I can still choose from my classes works.
Oh, right. Yeah, that's a good point.
Because that one I need to say that if I had my collection term B, and then how do I get from this at B to get an element from each? That one has something, which it may be doable because they're all small, but I would have to think about it. It definitely gives you case 2, but it may not give you choice from classes.
Right.
So it may not give you Fodor and Soloway.
And Cameron, remind me, we know that those are not equivalent?
They're not equivalent, but I don't remember exactly how the structure looks, what implies what.
Yeah, I'm also trying to remember this and I can't. Okay, yeah, I seem to remember that they're not equivalent.
It's my general assumption, if you give me 2 statements about the axiom of choice and drop power set, they're probably not equivalent anymore.
Yeah, Zarak has an old paper that looks at a bunch of these, but I find it, I don't know, it's hard to remember what's in the paper.
And it's rather difficult to read.
Yes.
Yeah, that's part of why it's hard.
So the last question on your on the last slide, what did you also mentioned something that I didn't catch, that you said something should be able to help you answer.
Well, I think so. The first question would be sort of to start off on this is, well, what is actually the consistency of this first sentence? So what is the consistency of a critical cardinal in ZFC without power set? And my guess is it's a weakly baby measurable. A weakly baby measurable should give you all of these things. You just don't necessarily have M as a subclass of V straight from the definition.
Right. So that's the problem. Getting the M,
Yeah.
that's when you said it, and I thought, okay, how do you do that? But all right, I have to think. I see.
Yeah, it's not clear that you get that, but this is definitely weaker than ZF, than a measurable, and it should be something around that, would be my guess.
Okay.
And if you then have those, because that's only you're looking at kappa models, or weak kappa models, sorry. So it's a model which is enclosed under sequences of length kappa. So just from the idea of it, there's no reason that V kappa should be a set.
Mm-hmm.
If you just take it all naively. So this would be where I would first look, and I've tried looking, and I'm currently thinking about it and not getting anywhere.
Okay, I see. Yeah, I will think about that too. That's really interesting.
Yeah. Because
Okay.
it would be quite cute if you can have a critical cardinal and the power set of omega is a proper class.
Yes. Anyone else has any questions? Okay, if no, I will stop recording. Richard, thank you very much. Again, really, really interesting talk. I love your open questions. I have to think about them. And if you could email me the slides, that would be great.
Yep, I'm doing